Okay, so I'm going to read through this question, and then we're going to break it down piece by piece. So they tell us that triangle ABC, right, here's the points A, B, and C, it forms a triangle inscribed, or that fits inside, circle O. They named the circle O because O is the center of the circle right here. Secant is a line, EFB. A secant is just a line. You can see the line EFB here, right? This is a secant. It means that it's a line that crosses your circle twice. So that's a secant. And what do they tell us? It bisects angle ABC. That's significant because there's a really important theorem. It's called Thales Theorem. And it says if you have a triangle where one side is the diameter, right? If you then pick any other point on the circle that's not one of the endpoints of the diameter, what you get is a right triangle. And so here, A and C are a diameter. We know that here in the next line they say that secant EFB bisects angle ABC and intersects the diameter AOC at G, right? So it's not going through the center, by the way, right? The secant does not cross the center. But they're telling us that AOC is a diameter. So that means that triangle that we're talking about is a right triangle, and that this angle right here, ABC, is a right angle. Furthermore, we're told that it bisects the angle. Bisects means that it cuts the angle in half. So we know that this angle measures 90 degrees, and we know it's cut exactly in half. So therefore, we know that each part, or each half, is 45 degrees. That's really a key to this problem, and I'll write that down. It's Thales Theorem. So I'll write it over here. This is kind of where it comes into play. Thales Theorem. And if you're in a high school geometry class, at the least, I feel like you should go look up a proof as to how that works. I do have a video on that, but I'm sure there are many other resources out there as well. So, going on. They also tell us that EDC, right, is a secant. So let's just find that. EDC is this line right here. So it's another line, secant, that crosses the circle twice. Okay. The measure of angle E is 20 degrees, and the ratio of the measure of arc AB to BC is 3 to 2. Find the measure of BC and the measure of FD. So, okay, we're told that this angle here is 20 degrees. Excuse me. And we're told a ratio of two arcs. I'm going to write that a little bit lower because we'll need that. The measure of arc AB to the measure of arc BC is 3 to 2. We'll be using that in a little bit. And I would also write down, I want to find the measure of arc BC. What's the measure of arc BC? And what is the measure of arc FD? Here, what do these equal? Okay. So, what is aside from the Thales theorem, what's another key to this problem? Another big key, I think, is understanding how these angles are called inscribed angles, an angle that's formed by two chords, AB and BC, two lines that connect on the circle, and are not a central angle or an angle to the center, how they are related to the arc that they intercept. So angle ABC intercepts arc AFDC, right here, this long arc. And what's nice is that the measure of ABC, this angle right here, the measure of angle ABC will be equal to 1/2 the measure of the arc it intercepts, in this case AFDC. So we know the measure of angle ABC is 90 degrees. And we know that it's 1/2 of the arc it intercepts. So it's 1/2 of the measure of the arc AFDC. So that means that what? That the arc, well, to solve for it, multiply both sides by 2, and it's 180 degrees. So the measure of our arc, AFDC, is 180. And that, I feel like, is a really big moment here, because it tells us also that the measure of the arc ABC is also 180 degrees, right? Why? Because in total the arc has to add 360 degrees, and we already have half of that. So now we know something else. The measure of arc ABC is also equal to 180 degrees, right? Put the degree sign in there. And another key to solving this problem is how this angle E is related to the arcs FD and BC that it intercepts. And if you have a secant or a tangent and a secant, what's nice is that the measure of the angle E is going to equal 1/2 the difference of the arcs it intercepts. The bigger arc, BC in this case, minus the smaller arc, FD. It's equal to half the difference. So we're going to put all this together now. Once you know that you have a right triangle, once you know how the secant is relating to the arc's intercepts, the only other piece we need, and the third key, I guess, to this problem, is the ratio of the two arcs. Let's look at why that's important. Measure AB, that's right here, right? That's this arc, right? So the ratio of this arc to this arc BC is 3:2, right? 3:2. And we just found out that the measure of that arc ABC is 180 degrees. So, if it was a 1-to-1 ratio, the measurement of each arc would be what? Well, they'd be equal. It would be 90 and 90. But you know that AB, which is represented by the longer side in the ratio, is going to be slightly larger than the arc BC. And I'm going to use some basic algebra here, right? If the ratio is 3:2, then I'm going to say that we can think of the arcs as 3x plus 2x, and that adding up to 180, right? However long these arcs are, it's going to be 3 times that value and 2 times that value to get the total arc sum. And here I solve for x, add these two, 5x equals 180, divide everything by 5, and what we get is x is equal to 36. If I plug this value into what I said the values of the arcs are, 3x and 2x, what happens? Well, x is 36. So then AB is 3x, or 3 times 36, but we are concerned directly with BC. BC is 2 times 36, or 72. So we've got our first answer. It's 72. What about FD? How do we find that over here? Well, that's where the secant relationship comes into play. So now all we need to do is plug these values into our formula, right? So I'll do that right down here. So again, what we're doing is using this formula right here. We know the measurement of angle E. We're given that from the beginning. E is 20 degrees and equals 1/2 the arc BC, which we just said is 72 degrees, minus arc FD. And what does that equal? Well, we distribute the 1/2. So 20 equals 1/2 of 72 minus 1/2 of arc FD. 1/2 of 72 is 36 equals, right, 20 in the side minus 1/2 of arc FD. And we subtract 36 from both sides, and what do we get? Well, you haven't ran into trouble here. You might think, oh, this cancels out. Oh no, I have a negative 16. And we can't have negative values for degrees or arcs in the circle here. So have we made a mistake? No, because we have negative 1/2 FD. So just like we're solving for x, we want to solve for FD. I would multiply both sides by -2, right? That'll cancel out the 1/2, and it'll give me my answer here. So finally, arc FD equals to 32, right? And that's our answer to this problem. So to recap, what happened here? Well, we're dealing with a secant. So with a secant, one thing's going to be critical is that the secant, the angle here, formed by a secant and a tangent, or formed by a secant and a secant, is equal to 1/2 of the two arcs it intercepts, the difference of the larger one minus the smaller one, and that was this formula right here. We also need to know Thales Theorem, which says that if we have the diameter as the hypotenuse or side of a triangle, if we pick any other point on the circle and connect the dots, we get a right triangle. And we use the ratio they gave us and the angles they gave us, and we were able to then solve this problem. And I think the only last thing we need to know, I think, in getting to this was that we're given an angle here that's an inscribed angle, which is equal to 1/2 the length of the arc it intercepts. And we didn't use it here, but in case you had the situation where you're dealing with a central angle. The central angle intersects the center, and I'm sketching this so it's not very accurate, but O is the center, and this would be a central angle. The central angle is equal to the arc it intercepts. All right, thanks.